Hello everyone, I'm Xiaoyang Wang, a PhD student at the University of Science and Technology of China. I'm happy to present our recent work, FineMem, Breaking the Allocation Overhead versus Memory Waste Dilemma in Fine-Grained Disaggregated Memory Management. At the traditional monolithic server architecture, CPU and memory resources are tightly integrated within each node. To meet the growing demands of memory-intensive applications, monolithic servers are required to provision large amounts of memory. However, this often results in low memory utilization, as a large portion of memory may remain unused and unshareable to other auto-memory nodes. As a result, the rising cost of memory has made disaggregated memory an appealing solution. Disaggregated memory, or DM in short, decouples memory from compute. This allows memory to be dynamically shared across multiple compute nodes using high-speed networks like RDMA or CXL. As a result, the memory utilization can be improved with a shared large memory pool. However, RDMA brings new challenges for remote memory allocation. First, allocating memory from a memory node needs RDMA-related memory region registration. Involves several operations. Pre-fault the physical memory pages using a memory map and copies page tables into the RDMA NIC and generate on-device memory regions with arcades as capabilities for the following one-sided RDMA access bypass the remote CPUs. These operations are notably time-consuming and must run on memory node CPUs. For instance, registering 1 GB MR can take more than 100 milliseconds. And second, the RPC-based allocation adds extra overhead because memory nodes often have limited CPU power, as we don't want to reserve too much external CPU resources rebundled to the memory side. To give an example, in a DM-native KV store system, the on-demand registration method achieves only 20% of the throughput of pre-registered memory region, highlighting that frequent memory region registration during runtime is impractical. Even with pre-memory map, we don't need runtime registration. The throughput plateaus after 32 clients, indicating that the RPC-based approach becomes bottlenecked by the memory node compute power as more clients are added. To overcome these challenges, most existing systems allocate memory in coarse granularities from megabytes to gigabytes. This reduces allocation frequency and hides the overhead associated with DM allocation, like in DM KV store. Allocation with large block size can significantly improve the KV operation throughput. However, this coarse-grained management approaches can introduce significant memory waste, which is similar to previous huge page research papers, that applications with huge page always cause more memory blocks. We have the same findings in DM management. For instance, in DM QA store, using a 4 kilobytes allocation granularity can reduce memory fragmentation much more than coarser granularities, like 2 megabytes and 1 gigabyte. As a result, RDMA-based DM system faces a key trade-off. They must either deal with high allocation overhead or accept large memory waste with fine-grained or coarse-grained management, and the dilemma they often knows the memory efficiency to confirm the performance. So we tackle the question, can fine-grained memory allocation be achieved with minimal overhead? So this is our goal. Solving this question would reduce memory waste in disaggregated memory pools, providing a fine-grained and shared memory pool, while also can recover and reclaim the remote memory chunk allocation status when compute node failure happens in a different failure domain. To achieve this, we focus on three key challenges as we discussed: reducing MR registration latency and optimizing fine-grained allocations over network, and supporting memory recovery during compute node failures. So we propose FineMem, designed for fine-grained, high-performance memory management in RDMA-based DM. Its design is driven by three key elements. Firstly, removing MR registration latency based on global memory region while overcoming isolation challenges. And secondly, enabling one-sided efficient remote memory chunk allocation. And thirdly, ensuring memory metadata consistency during compute node failures. First of all, to hide the registration overhead, a straightforward approach is to pre-register the entire remote memory as a single large and shared accessible memory region for each computer node. In this configuration, each computer node can allocate fine-grained memory chunks by directly modifying the shared allocation metadata with one-sided operations. But sharing a single memory region can introduce isolation challenges. Since the memory region is associated with a single arcade, any user holding this arcade can access the entire memory region. This means that any entity can potentially read write to any other user's chunks, leading to privacy and security risks among nodes. And the metadata used for memory allocation is also unprotected. To solve this, FineMem uses RDMA memory window to isolate the memory chunk access and a per computer node service to protect allocation metadata. First, memory window is an RDMA mechanism built on registered memory region to allow for quick generation of fine-grained arcades at a rate of one memory window per microsecond. This approach provides fine-grained isolation between users, as each user can only access the memory window which it holds the corresponding arcades. And second, the trusted allocation service handles remote memory allocation requests with per core worker for users. They do this one-sided allocation instead of users directly for the memory allocation to ensure that memory metadata is protected from DM users' direct access. And second, to avoid bottlenecks in memory node CPUs, FineMem uses one-sided RDMA for remote allocations. However, this approach needs carefully designed metadata to minimize network overhead, especially compared to swap update-based allocation. For example, one chunk per entry may require checking every entry in the address space, with each check needing an RDMA round trip, especially CS. This results in unpredictable allocation times, especially for large allocations that span multiple chunks, like 2 megabytes allocations require about 500 compare swap, which is really costly. So to accelerate large size allocations and to reduce RDMA round trips, FineMem employs a two-layer bitmap structure. For large size allocation, it directly searches the first layer bitmap for the large allocation, and for small size allocations, it searches the first layer bitmap to locate suitable second layer chunk groups, and then retrieve the second layer bitmap to allocate free chunks for small size allocations. This first layer is named as section, and the second layer is named as span, and the basic block we named it as trunk. And a section and each span comprises 32 contiguous chunks and a 32-bit free map to track the allocation status of these chunks. And a section consists of 16 contiguous spans in the 32-bit free map, using 2 bits per span to indicate the span's status. Especially, span status 00 and 11 presents where the span is entirely free or full, and 01 indicates that the span is normally used where the span is partially allocated as smaller chunks, while 10 denotes that the span is contented, which means multiple allocators can currently target the same bitmap for allocation, so we don't use this status span in a high priority. With this setup, FineMem can search and allocate up to 500 chunks with at most 2 RDMA requests. To prevent memory leaks during computer node failures, FineMem uses redo logging on memory nodes written by computer nodes via one-sided RDMA to track which memory chunks are allocated to which users, so that if this user's computer node failure happens, we can reclaim the unused memory. However, achieving crash consistency in a shared bitmap-based allocation system presents unique challenges. If a crash happens before writing the redo log, it can mix up allocation bits from the crash status and the normal status, making the chunk unrecoverable. Even with other threads helping to write the log to the suitable log situation, file slow failures can still occur, leading to out-of-date update and outdated log entry. To address this, FineMem adds a 32-bit temporary log into the bitmap we discussed previously, allowing each allocation to be temporarily logged, and this log can help distinguish between transient and committed states in case of a crash. And any node can flash this temporary log into a persistent for log without blocking. And this flash is forced before the next allocation so that it can confirm that each temporary log can be finally flashed into a for log. And FineMem also includes a compacted timestamp in the temporary log and the for log to prevent consistency issues due to outdated entries, so we can use the timestamp for out-of-date detection. To summarize, FineMem is designed to efficiently handle fine-grained allocation in a way that ensures crash consistency, using log-free, one-sided RDMA verbs. For more technical details like timestamp design or bitmap design, please refer to our paper. Finally, we use a Cloud Lab cluster with 16 computer nodes and up to 6 memory nodes for evaluation. We compare FineMem with 3 state-of-the-art baselines: on-demand registration with RPC allocation, and pre-registered MR with RPC allocation or array-based one-sided allocation. Both of these baselines come from related works. And we have integrated FineMem with 3 types of DM systems: a user space, a memory malloc system, a DRM-based key store system, and a DRM swap system. These systems use FineMem's malloc and free functions to management remote memory. First, we use allocation macro benchmarks to evaluate FineMem's performance. We find that FineMem outperforms existing approaches across a range of allocation sizes from 4 kilobytes to 2 megabytes, and under various levels of node parallelism, scaling up to 100 client threads and 6 memory nodes. As a result, FineMem reduces the allocation latency by up to 90%. We also conduct a factor analysis to show the overheads of FineMem's design mechanisms. Compared to the baseline, FineMem introduces only a small external latency of up to 10 to 20 microseconds, even with up to 500 client threads. Next, we integrate FineMem as the memory allocation backend for the DMKV store FuseE with the SSBA workload. We find that FineMem reduces the allocation overheads in KV update operations and leading to a bandwidth improvement of up to 100%. By using smaller blocks, FineMem achieves high bandwidth similar to coarse-grained blocks while also reducing memory cost by about 40%. And finally, we integrate FineMem into a DM swap system based on FastSwap, using it as the backend for dynamic swap out page allocation. With fine-grained page allocation compared to static pre-mem map swap systems, FineMem improves memory utilization to around 70% and allowing more jobs to run concurrently in the disaggregated memory so that the job throughput increases by about 8%. In summary, to address the performance and memory efficiency challenges in disaggregated memory, we propose FineMem. It supports fine-grained, high-performance memory allocation through 3 key innovations: removing MR registration, enabling efficient remote chunk allocation, and maintaining metadata consistency. This allows DM systems to achieve low memory waste with minimal overhead. And the source codes are open sourced. So thank you all for your attention. If you have any questions, please feel free to reach out to me via the email. Thank you.